Here we continue earlier lecture, operators in quantum mechanics. Here we construct Hamiltonian or total energy operator. For that, we find the total energy of the particle moving in x direction. That total energy is E is equal to px square by 2m plus v of x, where v of x is the potential energy. Now we simplify this equation by multiplying psi on both sides. We get E psi is equal to px square by 2m plus v of x psi. Here we find the value of px square by 2m psi, that value as we find earlier, and it is minus h cross square by 2m dava 2 psi by dava x square. We substitute this value in this equation and we rewrite minus h cross square by 2m dava 2 psi by dava x square plus v of psi, outside bracket we write psi, equal to E psi. And it represents the eigenvalue equation for Hamiltonian or total energy. In that equation, minus h cross square by 2m dava square by dava x square plus v is an operator which operates on the function psi, which reproduces the same function multiplied by the eigenvalue of the operator, that is E. That is, this is an minus h cross square by 2m dava square by dava x square plus v is a total energy operator that is denoted by h x hat, and it is called as Hamiltonian operator for one dimension. Now we extend this operator in the 3 dimension. For that purpose, dava square by dava x square, that term is replaced by, in the 3 dimension, dava square by dava x square plus dava square by dava y square plus dava square by dava z square, and v is a function of r. That equation is, in the 3 dimension, the total energy of the Hamiltonian operator written as h hat or h cap equal to minus h cross square by 2m into bracket dava square by dava x square plus dava square by dava y square plus dava square by dava z square plus v of r. That is, h hat equal to minus h cross square by 2m del square plus v, and it represents the total energy or Hamiltonian operator in the 3 dimension. Now, here the del square is a Laplacian operator. That Laplacian operator is the bracketed term dava square by dava square plus dava square by dava y square plus dava square by dava z square. Then the above equation we also write in another form of the equation, and that equation we know, Schrödinger time independent wave equation. H psi is equal to E psi. Since on the one side of the equation you know h is the minus h cross square by 2m dava square by dava x square plus dava square by dava y square plus dava square by dava z square plus v of r. Outside total bracket we write psi equal to E psi. It shows steady state Schrödinger wave equation or time independent equation. The total energy operator we write h hat but not E, because the total energy is assumed to be expressed in terms of momentum. Here we construct the another operator term, that is the parity operator, denoted by the symbol pi hat. It is a special type of the operator, and we define when such an operator operate on the wave function psi of x, then wave function gets reflected in its own coordinate. It means this parity operator operate on a function psi of x, then what is the result? We get the same function reflect in its own coordinate, means psi of x will become psi of minus x. Means the parity operator we express in that form of the equation, pi psi of x equal to psi of minus x, since that function reflects in its own coordinate, x becomes equal to minus x. Now here multiplied term is 1, that is an eigenvalue of the parity operator. That value may be plus 1 or minus 1, and it depends upon whether that function is symmetric or antisymmetric wave function. Hence, firstly we find what is the eigenvalue of the parity operator. For that purpose, the same equation for the parity operator we express in terms of the general eigenvalue equation. That equation is parity operator pi hat psi of x equal to lambda psi of x, where lambda is an eigenvalue of this operator and psi of x is an eigen function. Here, using this equation according to the definition, pi psi of x equal to psi of minus x and pi psi of x equal to lambda psi of x, these two equations we simplifying here. Hence, firstly, we find if the parity is again operating on the function on the both side of this eigenvalue equation, then this equation becomes parity is operated on both sides. We write the parity operator which operate on that term, parity operator psi of minus x equal to, here is also operate on the other side, pi into bracket lambda psi of x. Now we simplify that term. Here, if the parity is operating on lambda psi of x, psi is the constant term, take the outside, and we write lambda pi psi of x. On the other side, here pi psi of x is psi of minus x, hence parity psi as it is, pi psi of minus x equal to lambda pi psi of x. Now again simplifying here, psi of minus x is the function, that function is used for the operation of parity operator. Hence the parity operator operates on that function. Again the function reflects in its own coordinate, means according to the definition of the parity operator, this term becomes equal to psi of x. And what is the other side? Here the pi psi of x, that value using the eigenvalue equation, it is lambda psi of x. Already here is outside the bracket is lambda. This is the lambda psi of x, lambda square psi of x. Here the psi of x is common on both sides, it get cancelled, and we get lambda square equal to 1. It means lambda is equal to plus minus 1. Now when lambda is plus 1 and lambda is minus 1, these are the two special cases. For The function becomes when symmetric and antisymmetric. It depends upon the parity is +1 and -1. This is the eigenvalue when it is +1 and when it is -1, how we explain that term. For case first, if lambda is +1, the parity is said to be even and corresponding eigenfunction is even function. Such a even function satisfies the condition. Parity operator operate on the function psi of x, since that function is even function, and the even function satisfies the condition psi even minus x equal to psi even x, means minus x, it becomes x. Then only the parity is said to be even and the corresponding function is said to be symmetric function. For example, if we choose the even function, that is cos x, then psi even minus cos x equal to psi even cos x, since minus cos theta is cos theta, and therefore it satisfies that condition. Other example, even degree polynomial terms x square, 2x raised to 4 minus x square, ground state wave function for one-dimensional harmonic oscillator. All that functions are symmetric function under lambda equal to +1, means the parity is said to be even and corresponding function is even function. For case 2, when lambda is -1, the parity is said to be odd and corresponding function is odd function. It satisfies the condition parity operator operate on odd function, hence psi odd x equal to psi odd minus x, but that psi odd minus x is not as a even function, it is minus of psi odd x. Examples, if we choose odd function is sin x, here psi odd minus sin x, then what is minus sin x? It is minus sin x. We write here the function is minus psi odd x. Hence the sin x is a antisymmetric wave function. Other examples, odd degree polynomial terms, that is x, 2x cube, 3x cube minus 2x. All such terms also show antisymmetric behavior. Other example, odd wave functions for one-dimensional harmonic oscillator. All these are examples for odd parity, and the corresponding function is said to be odd functions, and they must be antisymmetric nature. Now we construct another operator term, angular momentum operator, denoted by the symbol L hat. In classical mechanics, angular momentum L of the particle is defined as R cross P, means vector L equal to vector R cross vector P. R is the position vector. That position vector you know, Ix plus Jy plus Kz, and linear momentum vector Ipx plus Jpy plus Kpz, and we take the cross product of the two vector, we get the resulting vector angular momentum vector. Here position vector and linear momentum vector term. If we take the cross product, then cross product of the two vector we express in terms of the determinant as the resulting L angular momentum. Also, we express in terms of the component ILX plus JLY plus KLZ, where LX, LY, LZ are the component of the vector L along X, Y, Z axis respectively. Then how we find these components? That we simplify the cross product of the two vector term, and cross product of two vector expressed in terms of the determinant. Since position vector are Ix plus Jy plus Kz and vector P Ipx plus Jpy plus Kpz, we write Ijk. What are the coefficients of unit vectors for position vector R, and for linear momentum vector P, we write its coefficient. Firstly, for position vector, components are x, y, z, and for linear momentum vector, these are the components along x, y, z, and coefficient of ijk, px, py, pz. Now we solve this determinant, and we get again solving the determinant again in terms of the ijk, and we get the component of the vector L along x, y, z directions. These components we express here. Lx means how we solve the determinant? Vector I multiplied by ypz minus zpy. This is the Lx, and that Lx is one of the component along the x-axis of the vector L. Similarly, Ly. How we find the Ly? Since it is the coefficient of the vector j, that we find zpx minus xpz. Is we write Ly zpx minus xpz. And what is Lz? Lz, this is the component along the unit vector k, that we write here xpy minus ypx. xpy minus ypx. Now here we get the three components Lx, Ly, Lz in terms of the momentum, linear momentum component Pz, Py for Lx, Ly for Ly. There are the two linear momentum components Px, Pz, and for Lz component, two components we write here Py and Px. Hence we firstly know what are the values of Px, Py, Pz linear momentum operator terms, and that value you know. Px is minus ih cross dab of dab ix, Py is minus ih cross dab of dab y, Pz minus ih cross dab of dab z. Now we put the value of Pz, Py and find what is Lx. Similarly find Ly and Lz. Hence, using linear momentum operator terms, the operator Lx, Ly, Lz are, we write here, Lx operator equal to minus ih cross into bracket y dab of dab z minus z dab of dab y. Since we put the value of here Pz and Py, minus ih cross take outside. Similarly find Ly operator, minus ih cross into bracket z dab of dab x minus x dab of dab z. Similarly, Lz operator equal to minus ih cross x dab of dab y minus y dab of dab x. And that equation represent here angular momentum operators along x, y, z axis. That equation we write equation Z. Now we express these components when get transformed into the spherical polar coordinates r, theta and here is phi. Hence, x, y, z term we express in terms of r, theta and phi. Hence, we put x equal to r sin theta cos phi, y equal to r sin theta sin phi and z equal to r cos theta. Here, using the spherical polar coordinates, we find the another relation of the angular momentum operator components Lx, Ly, Lz in terms of r, theta and phi. Hence, we simplify the equation z if we know each and every term in that equation means dev of dev x, dev of dev y and dev of dev z. That dev of dev x, dev of dev y and dev of dev z we write in terms of r, theta and phi. Hence, we write the substitution x equal to r sin theta cos phi, y equal to r sin theta sin phi and z equal to r cos theta. Now, how we express the x, y, z again in terms of r, theta and phi. Hence, we write here the r square equal to x square plus y square plus z square. Find cos of theta. Cos of theta from that equation we find cos theta equal to z by r. But r is again under root x square plus y square plus z square. Then find phi term from first two terms. If we take the ratio y by x, then r sin theta get cancelled. Remaining term is sin phi by cos phi, that is tan phi, that is y by x. Now differentiate r, theta and phi with respect to x, y, z and find the separate terms dev of dev x, dev of dev y and dev of dev z. Hence we find each and every term dev of dev x firstly, dev of dev y and dev of dev z. Now how we find this value dev of dev x? By using the equation dev of dev x equal to dev of dev r into dev r by dev x. Then the same term we differentiate with respect to the theta, dev of dev theta of dev theta by dev x plus dev of dev phi of dev phi by dev x. Similarly, find dev of dev y and dev of dev z. These terms are written as like. Now, as we know, dev of dev x we simplify from the earlier term r square equal to x square plus y square plus z square. Differentiate this term with respect to x only and put the value here. Again differentiate with respect to r and simplify the first term. Similarly, second term, as we know the theta term, what is theta? Cos theta equal to z by r. Simplify this term, differentiate with respect to x and find dev theta by dev x. That value again differentiate with respect to theta. Third term, dev phi by dev x. Since tan phi term is known, that is y by x. Differentiate phi term with respect to x, substitute value here and differentiate again with respect to phi. Total term is dev of dev x. Similarly, we find dev of dev y and dev of dev z. Therefore, the x component angular momentum operator term that we write earlier minus IH cross into bracket y dev of dev z minus z dev of dev y. Here we substitute dev of dev z. If we simplify this term, substitute here. Similarly, dev of dev y, that value we find from that equation and put the value here. If we find dev of dev z and dev of dev y in terms of r theta phi and put the value here, we write directly x component angular momentum operator Lx hat equal to I h cross into bracket sine phi dava theta plus cot theta into cos phi dava phi. Similarly, we find y component angular momentum operator Ly hat equal to I h cross into bracket minus cos phi dava phi plus cot theta into sine phi dava phi. Similarly, z component angular momentum operator Lz hat equal to minus I h cross dava phi. Now, these are the values we express in terms of r, theta and phi. This is the homework to you. You can find this value and prove that the Lx equal to I h cross into bracketed term, similarly Ly and Lz here. Now, we'll take the square of total angular momentum. That L square operator is equal to Lx square plus Ly square plus Lz square. How we get? Since L operator into L operator, that is L square operator equal to Lx square plus Ly square plus Lz square. Lx term is known, Ly term is known, Lz term is known. Take its square, that value you know. Take square of each term here and put the value and simplify. We get L square operator equal to minus h cross square into bracket 1 upon sine theta dava theta into bracket sine theta dava theta plus 1 upon sine square theta dava square by dava phi square. This value is for L square we express in terms of r, theta and here is phi. These values we use to explain the next term in that topic. Also we use Lx, Ly, Lz terms for the next explanation of another term. Thank you.